Challenge 4, okay. Okay. Oh, okay, good. Good deal. So.
Exam next week.
Yes. Next Wednesday.
The exam is
I'm sorry, the exam's Friday, yeah. The review is Wednesday.
3 tests in one day.
3.
You'll get that sometimes.
Yeah.
I got 3 on that day.
3.
One the day before that.
I'll try to make this one the best one. How about that? Whatever that means.
What classes?
What?
DE, digital devices, data structures, and the day before that I got Cal 4.
Good luck.
Hey, man, you don't need to sleep every day.
Yes.
Nah, I'm gonna go to shoot at 10:30. I don't need to
It's fine. You can stay awake for like a week at least.
Yeah. Come on, you're in college.
So we're going to do applying data structures today, and that's mostly to prep for a quiz that we'll do on Monday that is just about choosing which data structure applies in certain scenarios. So we'll talk about that. I'll show you some samples of how the questions are phrased. I'll tell you about some of my objections to some of the questions, but I can't change them because they're department standard.
This is for AVET, right?
Yeah. And so it's nothing like super different for you guys. It just counts as a quiz grade, just like any other quiz. But please come do it. Please come do your best, just so that we can get that measurement. Then we've got the rest of the semester here. So after we finish, next week we'll do the quiz at the beginning. We'll do the exam review in the middle. Then we'll do exam 3. We won't have class the week of Thanksgiving. And the only other class day we have is December 2nd. Currently, I don't think we'll have class then. I'm just kind of waiting to hear in case there's something I'm unaware of that we need to cover. But you'll definitely know during the holidays at some point, I'll have like your exam 3 grades posted, and you'll know if the optional final would be beneficial to you or not at that point.
Safe to say that the Monday quiz isn't going to be self-graded?
It will not be self-graded. So we'll do it kind of more exam-like, I guess. I don't know. But it'll also mean that we won't be here for long on Monday, so you'll come in, take the quiz, and leave. So.
Are we going over what the quiz on today? Or?
Yeah, we'll talk about it today, yeah.
And that quiz is next Monday?
Yes, yeah. All right, so last time we talked about hashing. And if you remember, the basic idea was we had some data that we would associate with a key, whether that key is the data itself or some other key that we've paired with it. We take that, which could be anything, any string of bits, put it through a function to map it to a discrete space, like an array, where we can look it up in constant time. So we had some examples of very basic hash functions. So in this case, just like taking a number value for each character in a string, adding it up, doing a modulus of the number of entries. And then we kind of quickly ran into this problem of collisions where, different strings would come out with the same key. And that brought us to kind of the biggest part of hashing. And specifically, I should say, like when when we hash the data and we store it, it's a hash table. So when we have these hash tables, when we have collisions, there are different ways to deal with it, and we'll always have collisions. We try to design the function so that we have as few as possible. One idea of dealing with it is like instead of storing just a single value in that table, is to store a linked list. It's a pretty good idea most of the time, unless you get just one really long linked list, and then of course that makes things inefficient. We talked about a maybe slightly better idea, and we looked at linear probing, which was a way to say if I have a hash of something and I go to put it in the table and there's already something there, essentially I'm just going to look for the next empty slot and put it in that slot. And so we went through some examples of that. seeing how even though these keys are the same, they've just kind of been moved to the next available slot. And so this is a good way of dealing with things in terms of you don't need to allocate like a linked structure that's separate. You're using just the memory you have here. But it is a lot of like kind of bookkeeping operations going on anytime you want to like delete a value that's in here or change anything. And then we also talked about like instead of doing this like in a linear fashion of just going to the next one, you could jump like, I don't know, like x squared or something, you know, to try to balance things out. So today we will talk about the applications of data structures overall. So we'll kind of start where we started this semester and work our way through. So here's a little bit of information about the quiz that you'll have on Monday. So it's 21 questions, and the way it's structured is each question is a sentence or two, and it's a scenario, and it will ask you to choose from these data structures, and these are just all the data structures that we've covered in the course. And so you'll just choose the best data structure that fits the scenario. So we'll start by kind of rewinding all the way back to linked list. And if you remember, this is like our most basic data structure, like only a little bit, I don't know, kind of, you've got the array, I guess, which is like what you would think of as like the most basic chunk of memory. The linked list is not far apart from that, right? So the idea being that, you know, rather than having to store everything contiguously, we could point to things and we could jump around and have things that had links to the next element or back to the previous element in some cases. So this idea of being able to have a piece of data that is able to point to another piece of data in a linear fashion, but maybe not fitting linearly into the actual memory. And so this is kind of a foundational structure. So this is what a lot of the other structures are built on, and we've seen that as we've gone through the class. This idea of linking, you know, pieces of data together with pointers. So if you remember some of the basics of the linked list, there's the idea that you can, you know, if it's a doubly linked list, like you could add to the end, you could add to the front. You could easily traverse through the list in a linear fashion, which is a little bit slow in comparison to some of the other things we know about. But it's useful. And we kind of went through the details of this, like how to remove an element from the middle, right? You just have to change these pointers around. So that's actually pretty efficient. It's like a fixed number of operations. Thinking about the applications of linked list, and I know we've talked about some of them as we've gone through these topics, but the main one for linked list is just other data structures. Lots of data structures are built on the idea of linked list. Kind of in the CS area, things like version control systems, so like where you have a snapshot of like a code base, right? And then changes are made, and now you have another snapshot, and it's a linear progression, so it lends itself nicely to that. Another place that we see it used frequently is anything that has like a linear playback, like media. So like you can think of a playlist of like music, right? Like a Spotify list or something. It can be done with a linked list, right? Especially because for the most part, the default mode of operation is right skip forward, right? So you're just jumping to the next one. You're not needing to randomly access necessarily. So that's kind of a common application. Like animation, so if you think about like very basic animation, kind of like the equivalent of when an animator would draw each frame on a piece of paper, right, and sequence them one after another, that can be done with a linked list structure, right, because you pretty much always want to play through that in order, and you might want to work on a specific one, you might delete something, but the linked list structure works very well there. And then we get into other things, any kind of feed, right? A dashboard, social media feeds, stuff like that, where things are linear, like, you know, just a list of things. A linked list structure is pretty much what's used. And I mean, I think it's a fair point that, you know, in your career, if you go to write software, you'll probably never like directly use the linked list or implement a linked list, right? But a lot of the things that you use, like whether it's a database or some collection library that's already in the language you're using, the linked structures are what's being used underneath. And so there will probably be like a few rare times where it does matter and you remember like, oh yeah, that's how things are linked and can actually help you solve a problem. And I think that's I think with this class, a lot of it feels very abstract, right? You're looking at it and you're like, well, I can solve a lot of practical problems without these things. But it's kind of for the rare times where you're deep into something or you're trying to optimize something and then you remember how everything is working underneath it. And because we kind of live in a lot of abstractions have been done for us at this point, right? We're pretty far from the beginning of things. So it's good to have that in mind. In the operating system level, so memory management is a big application for a linked list, right? So if you think about like just RAM in the computer, you allocate a chunk of memory for something, and maybe another process allocates a chunk of memory, and then one gives some up. You don't want like all those fragments, right? Because you waste it. With a linked structure, you can just point, and hop over those. So it's a pretty fundamental use there. So yeah, keeping track of the free and occupied blocks in memory, and mainly because it is just a linear structure, and that's kind of what we have to work with. So in terms of like the media playlist application, right? And this could be any kind of thing that's sequenced, right? It's just the idea of it is easy to move forwards and backwards. So those kinds of applications. Okay, so if you remember after linked list, we moved kind of briefly to stacks and queues, which stacks and queues are pretty basic, again, but they do have quite a few applications that are really useful. So if you remember the stack, the principle of last in, first out, and just thinking about like any kind of like real stack, like stack of paper or something, right? You put a piece of paper on top, the first one that you take off the top is the last one you put on. So, and the basic operations being push and pop here, and typically the ability to kind of look at the top without taking it off. So you could like look at the piece of paper but not remove it. And then kind of the complement to that is the idea of a queue, which is the basic first in, first out. I guess in the US we would call it a line usually. A lot of other places would just call it a queue, and it's very straightforward mapping, right? You get in line for something to wait. Whoever's there first is the first one to, get through the thing and then go on. So same thing, in queue, DQ, and just kind of the first in, first out there. The applications of stacks that we want to think about and kind of remember is, first of all, kind of relevant to challenge 4 is like the stack of like calling methods, in software, right? So keeping track of which function called this function and where you need to go back to return. So that's pretty fundamental. So also things like evaluating expressions. So like mathematical expressions, parsing things. Anytime like you want to match like parentheses or something like that, stack can be very useful. Obviously like manipulating text, doing things like maintaining state that you want to be able to get to. So like in the web browser, you can think of like as you navigate, you click on a link, it gets pushed on the stack, right? You push the back button, it pops one off the stack. Pretty basic. Undo and redo, pretty much in anything is going to be implemented with the stack. Things like photo filters. So if you think about like some of the popular like social media apps that have a lot of filtering functionality built into them, those will actually typically like stack on top of one another. And so that's kind of the structure that can be used there. And then pretty interesting in either 3D graphics or even in like, if you're doing automation like robotics or something, the stack is used to maintain context. So I'll talk a little bit more about it, I think, in another slide. But one of the main, I think probably the most popular application that we like see all the time of the stack is undo and redo, right? So there are different ways to set this up, but you can think of it just as having like two, let's say image and undo stack. I think it should be imagine. That feels better. Okay. So if you imagine an undo stack and a redo stack, you can kind of take the concept of like when the user does something, you push that action onto the undo stack, and with the idea that like you need to have an inverse of the action, whatever it is, you need to be able to reverse it. So it does depend on the application a little bit. But then whenever the user actually requests the undo, you actually pop that off, do the reversal, and push it onto the redo stack, so that you can continuously do like Control Z and Control Shift Z over and over and pop back and forth. It's just a stack, two stacks passing things back and forth. So that's a pretty common use of the stack. So kind of one that I find really interesting is the use of the stack in graphics or in like robotics. So you can think of whenever you're, like if you have a robotic arm, right, it's got like links in it, right? And so you usually have like an angle for each joint. If you're, either maybe you're just rendering that in 3D or you've got the actual thing, when you're here, if you move this, it affects the positions of everything down the chain, right? And so you can use a stack to push your context as you move down, whether you're drawing that or manipulating it. And so it's really just like, you've got these matrices that are transforms that are happening, right? And as you move through this hierarchy of objects, you are pushing or popping those. And it kind of is it gives you a nice way to do all of these things without having to consciously think about the context that you're in. You're always like in a local frame of reference. And so it's another place that like, you don't always realize the stack is part of it, but it definitely is. Another place you see this, I don't know if you do any like web development stuff and you have like an HTML canvas element, it's a pretty common thing to do like the canvas context and do like a dot save and then do some more and then return back to the previous context so that you can do these transformations. Another kind of very like satisfying way to use a stack is for evaluating math equations. So you can, this works well in a couple of different ways, but for like what we typically think of as like an equation that we would write down as the infix notation, we can use two stacks, one for operators and one for operands, and we can actually just parse those equations very easily by pushing them onto the stack and then popping them off and performing those operations. So now thinking about queues instead of stacks, a queue again is like just this generic thing that I'm sure you can imagine like a ton of them. So one that comes to mind like in terms of a lot of what we use today is we have a lot of content moderation for all of these platforms that we use, right? So all the user-generated content is typically like being classified by something, and if it needs human review, it gets put into a queue, right? And somebody sits there, and that's their job. They take the next thing off the queue. They decide if it's okay or not, and then keep going. Same thing with like messaging apps, anything like if you're trying to buy a parking permit for campus, right? You can like get on the website, and it'll tell you your number, whatever, and then it'll break. But the idea being like you're in this waiting list, right? The printer, like a networked printer, it's a pretty good example, right? You can send jobs, everybody on that network could be sending jobs there. Any kind of like job queue application. Also kind of an interesting like specific use of queues is for like traffic simulation. So if you are like someone who is designing intersections in a city and trying to route things, you will model a lot of this, like intersections as multiple queues, and then you can run simulation steps, to process the vehicles. Okay, so after stacks and queues, you remember we briefly started to talk about trees in general, not a specific kind of tree, just a tree in general. And the idea was it was like the linked list, except suddenly we could, point to more things than just the next one or the previous one. And we got a bunch of terminology there. We had the parent, the children, the ancestors, the descendants. And you remember at first we were looking at things like you could have however many children you wanted, right? But the idea being that it's like this tree-like structure, upside down tree, but tree-like in nature. And so we quickly kind of focused in on the binary tree, right? The trees where you can only have 2 children at most. And then from there, we pushed that a little bit further to add another constraint where we said a binary search tree, right? And so this added a constraint about how these elements relate to each other, so that if the value on the left child is always less, and the right child is always greater. And so there's that basic idea of binary search trees. And this was nice because, as we learned, this actually makes it much faster to search for things, right? Because every time we make a decision, we've cut it in half, kind of. And so we saw that, like, if we had this linear structure, this is a big theta of n, whereas with the binary search tree, if it's balanced, we have a big theta of log n. So big improvement there. And of course, we initially were not balancing these trees, right? And so we could end up with this horrible structure that's just a linked list. So we quickly kind of arrived at the idea of balancing those. And if you remember AVL trees, where we had the rotations, which was just a scheme that let us make sure we kept everything balanced and didn't have any one branch that went off too far. So, applications of binary search trees. Some pretty important applications in terms of like database indexing, so being able to sort keys of different data. Things like the file directory, right? Other things like network routing, even spell checking and text prediction, right? You can think of going through a binary search tree to predict a word. So using like the letters to make that decision to go to the next node. So searching through an ordinal database. So if you've got a database of things that are ordered and the meanings have value like relative to each other, then a binary search tree is a very efficient way to do that. So one thing that you do want to remember is that if you have like a large number of records, right, that you're storing, and they have ordinal value, the binary search tree is beneficial if you want to run queries like look for everything greater than 7, or something that's going to return a lot. If you're just looking for a single record, like in a large collection, the fastest way to do that's going to be a hash table, right? Because it's a hit or a miss, right? So for the quiz that you're going to take, despite its wording, I would like you to remember that if ordinal databases are mentioned, you are doing a binary search tree, despite the lack of specific wording that tells you so.
Is it gonna be multiple choice?
It will be multiple choice, yes.
Alright, that's cool.
Yeah.
So it's just picking those things for all 21 questions?
Yes, exactly.
So what you're saying is there's a question, even though hashing is a better tool for searches, I'm gonna choose binary search tree if I see the word ordinal.
If you see that, yes, that is a great way to say that. Yeah. So the question hints at this ordinal thing, but it doesn't say it quite right. But yes, choose the binary search tree there, please. Other things you could do with a binary search tree is kind of prefix decoding. So again, this is like with the text prediction example. You can think of going down that tree to each letter and being able to make a prediction at a certain point. You can also think about decoding a binary value by going down the tree. And so if you had like, a string of zeros and ones, you might start at the root and then for each 0 go left, each 1 go right, and arrive at some value. For the balanced binary search trees, these are kind of the examples we talked about when we covered it. A lot of the same things. Obviously, there's some overlap in terms of like file systems and stuff like that. But generally, a binary search tree is very good for things where you have these relative comparisons. Right. So then we moved on from the binary search tree, and we moved to the heap, if you remember, which is also a priority queue. It's another name for that. And so the idea here was that we had this different relationship that we enforced. Instead of like the smaller one being on the left and the greater one being on the right, we cared about either like doing a min heap or a max heap, keeping either the maximum element at the top or the minimum element at the top. And you remember how we worked through different ways of processing that if you removed something and needed to resort that. So min and max heaps, and those are the two properties that we had there. And remembering that these are also called priority queues. And really, it's kind of arbitrary whether it's like min or max, because you can think of it either way, like a low number has a high priority or a high number has a high priority. But these were the general properties that the heap keeps enforced, and that's for the max heap, the parent is always greater than the children. For the min heap, the parent is always less than the children. And if you remember, they had this nice property where we could put them into arrays with just like this formula. So it's kind of efficient because they're always these complete trees that we keep organized. And we had the idea of doing a heap sort. So the idea being if we put like an arbitrary collection of elements into this heap structure, we could just keep taking one off the top, and that would sort it because it would either always be like the max or the min. And we talked about a couple of ways to do that. And so there's kind of seeing that structure and how it maps out into linear memory. Same thing for the min heap. So applications of heaps or priority queues. You can imagine these are pretty much the same as like queues, right? So anywhere you could use a queue, think about a priority queue as just being able to take whatever's in that queue and make some exemptions or some special circumstances for specific elements to move them through the queue faster than just as they arrive. So we see this, like the big one in an operating system is just to decide which task is going to get priority for CPU cycles, right? So if the window's in focus and the user is trying to like click through things, obviously that's more important than like the thing that's analyzing faces in all of your photos and trying to tag them for you, right? So priority queues show up a lot there. They get very complicated, obviously, with like modern operating systems. Where we see it like more in kind of like just real-world applications that don't even have to be computing necessarily, are things like event management and things like when you're just prioritizing like resources getting into an area or something. So obviously any kind of real-time like gaming or anything like that is going to use that. Also, when we have like all the apps that deliver things to us or pick us up or do whatever, right? There are different priorities that are weighed, so it's not just like a simple queue. There's a lot of factors that go into it. And so some more like technical kind of implementations, things like load balancing, maybe like web traffic or something hitting a server. And that might just be as simple as you want to like distribute out that processing load, right? You don't want to bring down any one machine, something like that. Same thing with caching data. So if you think about, like if you're a network that needs to distribute like a bunch of content like Netflix or something, right? And you've got all these data centers in different places, what things do you keep cached like in RAM versus solid state versus offloaded somewhere else? So all of that, priority queues or heaps, part of that. Some kind of day-to-day example, if you think about the hospital emergency room, right? When people come in there, it's not just first come, first serve. You usually take whoever needs care most urgently first, right? So kind of a triage idea. Same thing with like customer service relation management. So some customers are more important than other customers in a lot of cases, and might get priority. And then of course, CPU task scheduling, which we talked about. All right, so that brings us kind of closer to things we've been looking at recently, graphs. And you remember we have the directed, the undirected graphs. I will not bore you with thinking about all of that because I'm sure it's fresh in your mind. We have weighted graphs, unweighted graphs, kind of these processes of depth first search or breadth first search for traversing the graph. We've looked at ideas like the minimum spanning tree for getting through the network or the graph in an efficient way. Finding the shortest path. We've talked about Dijkstra's algorithm for that. And we'll look at a lot more of that when we review for the exam on that. And then we talked about Euler paths and kind of solving some of these difficult problems. And also Hamiltonian paths and circuits, which are a little bit harder to solve. And some of those classic problems that go along with that, like the traveling salesman problem, where you need to satisfy these constraints. And you can model this as a graph, right, with weights. And these are things that are pretty hard to compute in the like fully optimal way. We usually use some kind of estimation, some kind of heuristic that's close but not perfect. So, talking about applications of graphs. Graphs obviously have like very broad applications. Social networks are like the biggest kind of use of graphs. I think if you're really interested, you should look at like some of Facebook, well, Meta's research on how they manage like their social graphs, because there are like trillions at least of edges and things. It's very interesting from just an algorithmic point of view how to do that. So we've got things like social networks, connections between people, things within like our programming environments, like when do we need a resource? Yes?
I forget my bad. Are the edges the nodes or the edges the...
The edges are the connections between the nodes, so the lines. Yeah. And also sometimes vertices, right? Vertices / nodes, like a bunch of names for everything in graphs. But the idea being that like we could use this to find dependencies, right? So we could know if we need to like load in a specific module or something that we're using, and once we're done with it, we could throw it out of RAM and use it for something else. Knowledge graphs are really interesting, kind of with a bigger thing before like large language models, but the idea of like actually modeling out concepts, right, that are related, like semantically to each other. And we talked about some of these other things like doing things like fraud detection, surveillance, all kinds of things that you can do with a graph. Some of like the common everyday things that we see, GPS navigation apps, that's definitely a graph. Looking at like each location as a vertex or node, and then the edges connecting them. Obviously the social networks, and also things like, so maybe not even dependencies in software, but things like course prereqs, right? Like you can't take this course without taking that course. You can see how that becomes a graph pretty quickly. All right, and then we talked about hashing, which we've already reviewed today. And so let's talk about a few applications of hashing. So any kind of caching that you want to do, hashing is a great way to do that. You can kind of, so like a lot of web applications, which is kind of how like most content's delivered, right? If you want to put a resource somewhere, you can do that, create like a unique hash for it, pass that hash along out to users, and that'll serve that resource however long you have it there. Any kind of key value pair, right? Like so maybe like a phone book or contact list kind of thing, where you're looking for like a name mapping to a number or an address, stuff like that. If you're looking up like items in a very large inventory, right? You would probably hash like the little, like the barcode, the UPC number or whatever, into the database, and that would be a very efficient way to pull that record. Real-time analytics and e-commerce, which is a nice way of, yeah, there it is, tracking all the users everywhere all the time. So lots of hashes going on there. So like if you want to profile someone's like browser uniquely, right? You can actually like create a hash that represents specific things about their browser, like what fonts they have installed or graphics cards, or it's kind of like this huge cat and mouse game that goes on with like security versus, you know, being able to actually have things happen that we want. But you can use those things. You can even use like timing, how long it takes for a certain task to occur, hash that, and use that to represent a user and track them across things. So another use of hashing that we discussed is something like hashing a plain text password so that you don't store an actual password. So this is just like really basic Python code that is hashing the password hunter2 using bcrypt, which is a pretty good acceptable way to hash things today. And you get an output like this, right? And the idea, with a lot of other details involved, but the idea being if you see this or this gets leaked or whatever, you can't recover that easily. And as we all know, like most of the people who have built web services never did this right, and so like everything is compromised all the time. But this is an application of hashing because it's taking that original string and mapping it over into this space. And in this case, because it's a cryptographic hash, we can't reverse it, which is the goal. So another thought for Monday is that if you see a question that talks about passwords and storing them, I guess you could call that a hash table if you want. It's not a hash table, right? Because it's a hash. Hash table is actually yeah. But password hashing, right? Good enough, okay. So we talked about some of these other uses of hashing that are like actually very interesting because you don't think about them and like it's the thing that lets you do like find very quick, right? Searching for a substring and a larger string. And if you think about that, a substring and a string could be anything. Like a substring could be a term and a string could be everything on the internet. You know, you can scale that however you like. So
hashing is control F for it?
Yes, typically, yeah, control F will be implemented with hashing. Yeah. Other uses we talked about, checksums for files to detect corruption or tampering, and we talked about perceptual hashing. Okay, so I wanted to get to a few examples of how these quiz questions will be phrased. So these are just kind of similar to what will be on there. So like this first one, the scenario is that there's a call center handling multiple customer support calls. They're answered in the order they're received. What data structure is best for that? Guesses? A queue, yes. It's queue. Okay. So yeah, you know, they're kind of the key thing being in the order they're received, right? So another one, photo editing application allows you to undo, redo edits, and see your edit history. So which structure might you use for undo, redo? Stack, yeah. So this is kind of exactly, these are the formats that you'll see. There'll be just different details. Here you go, here's an example. So like disaster response, you have responders that are going out to find people in whatever this is, and they assess how badly someone's injured, and then relays this to the medical team. Medical team will treat the most urgent cases first. So what kind of data structure? Heap, yes, heap or priority queue, absolutely. Yes. And that'll be labeled as both of those on the quiz, so you'll, either one. Okay, so grocery store line. So let's see, you're just in the line at the grocery store, and whoever's first goes first. Queue? Yeah, just regular queue. All right, a couple more. So airport, you've got planes wanting to land, and we give priority to planes that are having like some kind of problem where they're going to fall out of the sky if they don't land sooner rather than later. What kind of? Yeah, priority queue or the heap, yeah. Okay. And then how about a library catalog? We've got a bunch of books, thousands of books. I think it should be more than thousands, but so you've got a lot of books, and you want to be able to find out information based on like the ISBN of the book. Yes, hash table. Yeah. Okay. And that is all that I have. So we will meet on Monday. We will have this quiz. It's 21 scenarios like that. You'll pick them out, and then that's all we'll do. So it should be a pretty short class. But other than that, have a great weekend.